All right, hello everyone. Thanks a lot for watching. So this is about some recent joint work with Sam Fiorini, with Gwenaël Joret, and with Yuditsky, who are all from Brussels. And it's actually an outcome of a longer series of papers together with Michele Conforti and Tony Nguyen. All right, so this is about integer programs of a certain type. And our work is motivated by the following open question in integer programming that is currently very actively discussed. So the question is there a polynomial time algorithm for integer programs of a special form? So a general integer program here is defined by a system of linear inequalities in variables x, a linear objective that we want to maximize, and all variables are required to be integer. Okay? Now, of course, such integer programs are hard to solve. You can model any NP-hard problem with that easily. But what about the following class of integer programs, where we require that the coefficient matrix A is integer, has integer entries, okay? And now the actual requirement is that all the subdeterminants of this matrix A are bounded by a constant. So what I mean by this is, you go over all the determinants, absolute values of determinants of square submatrices of any size of A, so even single entries, okay? And they are all bounded by a constant that we will always call delta here in this context, okay? All right, and again, the question is, if delta is a constant, can you solve such integer programs in polynomial time? And this question is quite open at the moment. So what do we know? So one of the first things that you learn in your integer programming class is this conjecture or this question is true if delta is equal to 1, in which case we would say that this matrix A is totally unimodular, and what you learn is that essentially you just have to solve a linear program, and basically if you end up in the vertex you see that this is already an integer optimal solution. All right. Recently, there has been a very nice paper by Artmann, Weismantel, and Zenklusen who show that this question is also true if delta is equals to 2, okay? Which they refer to the bimodular case. So this is the totally unimodular case, and maybe this is the totally bimodular case, okay? Where this is pretty easy, this is highly non-trivial, okay? So this is a very strong paper. And again, they show that the answer is yes if delta is equal to 2. Okay. However, the question is entirely open if delta is equal to 3, 4, 5, whatever. Okay, so for any constant larger than 2, we don't know the answer to this question. Okay. The main result of the paper that I'm presenting today is that the answer to that question, if yes, is yes, for all delta if we put a further restriction on A. Namely, the answer is yes if every row of our matrix has at most 2 non-zero entries. Okay? Or, the question is also true if every column of A has at most 2 non-zero entries. Okay? So note that, here we still require that all the subdeterminants are bounded by delta. If delta is not a constant, right? Then also these special classes of integer programs contain hard problems. So if you only allow every row to have 2 non-zero entries, then you can easily model the stable set problem, and we will get back to this later, okay? So this is a hard problem. If you only allow 2 non-zero entries per column, then this is what people call the integer knapsack problem, which is again a hard problem, okay? So in this case, you cannot just drop this delta, right? We don't know if you need that restriction, probably not, but that's how far we can go, okay? So note that there is a row version of the statement and a column version of the statement. The column version of the statement is much easier. You can do this by reduction to B matching. Here we'll focus on the row version, okay, which is more interesting. Good. So we will also consider a related problem, which is a stable set problem in a certain family of graphs. So we consider a maximum weight stable set problem in a graph G, undirected graph G. And the family of graphs that we're looking at, they will have the property that OCP of G will be bounded by a constant. OCP of G is what we call the odd cycle pecking number, which is the largest number of disjoint odd cycles that you can find in G. The largest number of odd cycles that you can pack into G. Okay? So what has this number to do with like our setting? Here's a rather simple exercise. So suppose that in our integer program, let's say, suppose that A, the coefficient matrix A, is the incidence matrix of a graph. Okay? Then it turns out that the largest subdeterminant that you see is a power of 2, and it's actually 2 to the odd cycle pecking number of G. Okay? So why is that? Well, let's look at the graph. Let's draw the edge node incidence matrix of that graph, and then you will see that whenever you have an odd cycle, this creates a block matrix here, and if you check the determinant of that block matrix, that's plus or minus 2, because it's an odd cycle. Okay? And now, if you have several disjoint odd cycles, you will identify several blocks that all have determinant 2, and so you get that value. Okay? Aha. So let's think about integer programming versus stable set. So how do you model the stable set problem as an integer program? Well, you have a variable for every node, and then you essentially write down constraints like xi plus xj is at most 1 for every edge ij. Okay? So your coefficient matrix that you're writing down is essentially the incidence matrix of a graph G. Aha. So what does that mean? This means that if I have a graph with odd cycle pecking number bounded by a constant, then this means that the resulting integer program to solve the stable set problem is an integer program whose coefficient matrix has also bounded subdeterminants, right? Bounded by a constant. So this means that a consequence of our main result is that the stable set problem in the family of graphs with bounded odd cycle pecking number can be also solved in polynomial time. Okay. So let's say something about previous results on this problem. So note that if the odd cycle pecking number of a graph is 0, then this means that there is no odd cycle at all, which means that our graph is a bipartite graph, and in this case, solving the stable set problem is easy. From the work of Altman, Weismantel, and Senclusen, we can derive a polynomial time algorithm, or the work of them. This implies a polynomial time algorithm for the stable set problem for graphs with odd cycle pecking number at most 1. But this, previous to our work, was the only case where we knew an exact algorithm that runs in polynomial time for that problem. Okay, so even the case odd cycle pecking number 2 was open. Okay. However, when it comes to approximation algorithms, we had already quite strong results. Namely, there was a p-TAS following the work of Tazari. There was a p-TAS for any odd cycle pecking number bounded by a constant. Okay, and actually, if you want to have a p-TAS, you can even go further. You can push the odd cycle pecking number actually until basically square root of n. Okay, good. All right, but now we can get a polytime algorithm for every constant odd cycle pecking number. Okay, so here's the overview. Our main result actually is integer programs with bounded subdeterminants where every row has at most 2 non-zero entries can be solved in polytime, and I said that the corollary of this is that these stable set problems can be solved in polynomial time. However, our approach is actually a bit different than what you would expect. Our approach is that we first prove the corollary, and then we prove the main result. Okay? The main result, like once you have this, the main result is not too hard to obtain. It needs several arguments, but it's not too hard to obtain by several tricks that I would say are nowadays standard in theoretical integer programming, proximity results, refined proximity results that we have to prove for this case, and clever reformulation. Good. So today, that's why today we would like to, like in the next 10 minutes, I would like to give you just a brief idea. How do you solve the stable set problem on bounded odd cycle pecking number graphs? Good. The main motivation is a result by Lavache characterizing graphs with odd cycle pecking number at most 1 that are, sufficiently connected. Okay. And his result says that these graphs, they have a lot of structure. So either there is a very small number of nodes, namely at most 3 nodes, so that if you remove them, you get a much simpler instance, namely you get a bipartite graph, so things get easier. Okay. Or your graph has what they call an even face embedding in the projective plane. So all you have to remember is it can be nicely embedded onto a surface of a very small genus. Okay. So let's have a look at that case. So let's have a look at the case where you're faced with a graph that can be embedded onto a surface of constant genus. And we have to deal with some ugly surfaces, namely non-orientable surfaces. Okay. Then in some previous work that appeared at SODA, we showed that if you have such a graph and you deal with a stable set problem, then the two-sided odd cycles, they have a property which is called the Erdős-Posa property. Namely, what you can do is, by some enumeration, by some clever preprocessing, you can reduce to the case where in that embedding, every odd cycle, right, there are some odd cycles, corresponds to a curve that induces a Möbius band. So this curve in that embedding will be one-sided. Okay. So I know that this sounds crazy, but how can you exploit that? Okay, and this is actually easy. Okay, I mean not obvious, but I hope easy to understand. So I claim that locally your graph will be, it's planar, right? It's an embedded graph, but it will look like a bipartite graph. And why is that? Well, you won't see any odd cycles in here, because odd cycles, they correspond to Möbius bands. And so locally you don't see Möbius bands, right? Like you're in an embedding on a surface, so locally everything looks like the plane. So this is a bipartite graph that just comes from the previous strange property. Good. So if you have a graph that is embedded on a surface, right, you can look at the dual graph. Okay. And now, since this graph is bipartite, we can assign an orientation to the dual graph. We will choose a more or less unique orientation in the following way. Around every dual node, we will orient the arcs in an alternating in and out way. Okay, so here this arc is going out, this is going in, this is going out, this is going in, and so on. So in the cyclic order, it's alternating. And the fact that all the odd cycles correspond to one-sided curves will allow you to make this orientation in a consistent way along the whole surface. Okay. Good, great. Now let's go back to the stable set problem. Okay, so why is this useful? So let's look at the stable set. Look at all the edges that are disjoint from that stable set. Okay, so here the red edges, they have nothing in common with the stable set, so let's pick them. We call them slack edges. And now let's remember the dual graph. And so let's pick the respective dual edges or dual arcs. Okay, so let's pick all the dual arcs that correspond to edges that are disjoint to the stable set. So it's like these pink ones, red ones, okay? And forget about the remaining ones. And then what you observe is that all these red edges, they form a circulation in the dual graph. Okay, so circulation is for every node, the number of arcs going in is equal to the number of arcs leaving that node. Okay, so this is what we will call a 0-1 circulation in the dual graph, which means that stable sets, they correspond to 0-1 circulations in the dual graph. And actually, you can nicely characterize what circulations you're really interested in. And with some minor additional effort, what you can show is that instead of computing a maximum weight stable set, we only need to compute a minimum cost circulation with a few requirements. So first of all, it should be non-negative and integer. That sounds easy. So this is the classical min cost circulation problem, if you want. Okay. But in order to make sure that it corresponds to some node sets like stable sets, you also need a somehow topological constraint, which says that your circulation should be homologous over the integers to the all-one circulation. You don't have to know what that exactly means. The main message is that if you deal with such a problem on a surface of bounded genus, okay, which we have, then you can solve that problem using some clever dynamic programming. Okay, so the keyword is really how do you compute homologous flows. In our SOTA paper, we have shown how to do that, and actually later we have shown how to do that even simpler. So this works, okay? So this works. This is like the key idea how to approach such problems, okay? But now remember that we dealt with a graph on a surface of bounded genus, okay? But now if I give you a graph with bounded out-cycle pecking number, it's usually not embedded. You cannot embed it onto a bounded genus surface, okay? So therefore, in our paper, we have to spend a lot of effort into a structural result about such graphs. And the structural result, it's pretty complicated, but let me give you some idea how it looks like, okay? So again, there will be a surface of bounded genus. This surface is non-orientable, so these small things here, they should be cross-kept, so you will see Möbius bands. Okay. Some part of your graph is nicely embedded on that surface, okay, as usual. But there will be also some parts that we call large vortices, which are not nicely embedded. So they sit inside disks, okay, but they're not, I mean, they are drawn with crossings, okay, so they are almost arbitrary graphs. They have some nice structure, so they have some nice cyclic decomposition, which means that they have some nice cut sets. There will be also some small vortices. So the difference between large and small vortices is that these large vortices, they can intersect in an arbitrary number of nodes with the surface part of your graph. The small vortices, they intersect in at most a bounded number of vertices. Okay, and the number of large vortices, this is bounded by a constant. Okay, good. The number of small vortices is arbitrary. All right, there will be a bounded number of apices. Okay, that's fine. And then, I mean, of course, we focus on the stable set problem. So with some further preprocessing, this structure, I mean, so far this structure is nonsense because you could fit everything complicated just into these vortices. But with some more effort, we can assume with some preprocessing that all the vortices are bipartite. Okay, and this is a key ingredient. This is all quite, I must admit, complicated stuff. It uses several state-of-the-art graph minor papers. Okay, but all right, let's assume we have that. I mean, how do you do this? Like, how do you handle that? Well, first you take that structural result. You make sure that the graph embedded on the surface is nicely embedded as before. So you want to exclude the odd cycles that are two-sided. Good. Now you have these small vertices. When you have many of them, but you can actually replace them by gadgets, which was established by in an IPCO paper of ours earlier. Okay, you can replace them by gadgets, and now you use this homologous flow idea that I presented to you earlier. And now the main work that still needs to be done is make the original idea of the dynamic program work with now these large vortices which are still there, right? And this requires some non-trivial effort, but we managed to do this in quite a nice way. So in the end, it's still a dynamic program. All right. So so I hope I gave you a rough overview of like what is necessary to deal with stable set problems on bounded OCP graphs. Remember that this was all coming from a very nice question that I really liked from integer programming. So let me just repeat this. So is there a polynomial time algorithm for integer programs whose coefficients matrix is integer and whose subdeterminants are all bounded by a constant? As I said, this is still far open. So any progress on that would be nice. In any case, thanks a lot for watching. See you at FOCS.